In this video, I want to present a proof that there are infinitely many primes. This is a really classic result in math and one that we just can't help but talk about. This is, I think, one of the more important theorems that we'll talk about all semester. So it turns out that there are infinitely many primes. This is worthwhile talking about because if you write down the primes, it looks like they're really all close together, right? If they start with 2, 3, 5, 7, looks like lots of numbers are primes. But in a certain way, the primes get thinner and thinner and thinner, namely using the prime number theorem, which I'll talk about at the end of the video. And so when you get to the higher up numbers, say let's go to 89, let's see, 91's not, 93 is a prime, 97. So you can tell that, I mean, I've skipped some numbers here, but you can tell that they're starting to get more and more spread out. It can't be that, so for example, 3 consecutive odd integers, at least one of those has to be a multiple of 3. So if you take any 3 odd integers, say 101, 103, 105, at least one of them is a multiple of 3. So that can't be prime because it's got 3 as a factor. And so 1 and 1 and 103, I think both are primes. But you get these kind of considerations where you have to start canceling off more and more numbers. And so the primes get more and more spread out. And again, in a way that we can quantify, which I'll talk about in the prime number theorem at the end of the video. Now, despite them getting more and more spread out, it turns out that there's still infinitely many primes. And so what we're going to do is we're going to give a proof. This is not Euclid's original proof. This is kind of adapted from Euclid's original proof, but we'll give a proof by contradiction. Euclid's original proof was a little bit more subtle than this, and I'll talk about that as well. But the proof by contradiction goes as follows. Assume that there are only finitely many primes. So assume there are only finitely many primes, and let's give them names. So let's give them names, say P1, P2, P3, and let's go up to P sub capital N, where capital N is a million, a trillion, a billion, whatever. So whatever big number you want to put there. So assume that there's only finitely many primes. We have to now find a contradiction. And if we can find a contradiction, then that proves that there must be infinitely many, because if there can't be finitely many, there must be infinitely many. So classic proof by contradiction here. What we're going to do to find a contradiction, we're going to consider the number, I'm going to call it E in Euclid's honor here, but E is going to be the number P1 times P2. It's the product of all the primes, all the way up to Pn plus 1. So I want to consider the product of all those primes plus 1. And it turns out that, so what we'll show that either E is prime, so it's possible that E itself is prime, or E has a prime factor not in the list. Okay, and if it has a prime factor not in the list, well, that contradicts the fundamental theorem of arithmetic, which says that given any number, there's only one way to write it as a factor, as a product of primes. So if there's primes that were not on the list, then there's our contradiction. So this is our goal here. So we're going to construct a number that's not divisible by any primes in the list, and that number here is E. So now we need to think about why did none of the primes in the list divide E. So notice that P1, so let me write it this way. If P1 divides E, then it turns out that what that means is that P1 divides this product, P1 times P2, all the way up to P sub n plus 1. But if P1 divides E and if P1 divides this product, so notice that P1 definitely does divide this product P1 up to Pn, because you can factor out this P1 here, then it divides their difference. So then P1 would divide 1. But P1 is a prime, so that means in particular it's at least 2. This is nonsense. So what we can do is we can conclude that P1 does not divide E, because if it did, then it would also have to divide 1, which is impossible. So it can't divide E. Likewise, none of the other primes in the list can divide E. Okay, for any of the other values of I, those also can't divide E for the same reason, right? If they divide E, then they would also have to divide 1 using the same reasoning as before. And no prime divides 1, therefore it can't divide E. And this is enough to give us a contradiction, because what we just showed is that E is a number that's not divisible by any of the primes that we have on the list. So either E itself is a prime, in which case we missed a prime. In other words, the list was incomplete, so there's a contradiction. Or E is divisible by a prime that's not on the list. Again, that means that we missed one, and that gives us a contradiction. Okay, so this is enough to prove that there are infinitely many primes, because if we assume that there's only finitely many, we run into problems with the fundamental theorem of arithmetic. So this is a contradiction, and namely this contradicts, let me just write that this contradicts the fundamental theorem of arithmetic. Okay, so that contradicts the fundamental theorem of arithmetic, which gives us the uniqueness of product of primes. So every integer greater than or equal to 2 is either prime or a product of primes in a unique way. That's the fundamental theorem of arithmetic. The last thing that I want to do in this video is talk about the quantitative way in which we know that the primes get more and more spread out. And that follows from what's called the prime number theorem. The prime number theorem was probably the most important mathematical result that was proved in the 1800s. And what it says is that if pi of x is the prime counting function, so pi of x is the number of primes that are less than or equal to x. So for example, pi of 10 is 4, because you have 4 primes less than or equal to 10. Pi of 100 happens to be 25. Pi of 3.7 is 2, right? So this is actually a function that can take any real input. Well, any real input that's greater than or equal to 2 anyways. It doesn't really make sense to talk about pi of 1 because there are no primes less than or equal to 1. Anyways, pi of x is the prime counting function. And what the prime number theorem says to us is it gives us a asymptotic growth of this function, meaning we can't come up with an exact formula for this function, but we can talk about how it behaves long term. So long term, it looks like pi of x is going to behave like x over the natural log of x. So what that means is that if you take pi of x and x over the natural log of x and you compare them, these values get closer and closer to 1. So that limit, it turns out to be 1. That's the prime number theorem. Again, proved in the late 1800s by multiple mathematicians. So again, a very important result in number theory. This gives us quantitative bounds for the number of primes that we can have up to a certain point. Okay, so this is a way that we can actually talk about what's a maximum number of primes that we can have from 1 to a million or from 1 to a billion and so on. Okay, so this is a nice quantitative way to talk about this. In particular, I want to mention that the number of primes is infinity. This is a really, really bad way to prove that there's infinitely many primes, but it has that as a consequence, right? Of course, there must be infinitely many primes because this limit is 1. If there were only finitely many primes, this term would eventually just be a constant after a certain point, in which case, since x over natural log of x goes to infinity, this entire term would have to go to 0. So if this was a constant after a certain point, then this limit would have to be 0. So the fact that this limit's not 0 is, again, a way that you could prove that there's infinitely many primes. This is probably the hardest way that you can prove that there's infinitely many primes, or at least it's one of the hardest ways. Okay, but this is the prime number theorem.